If your physics teacher asks you in class what an electric field is, it will be enough to say that an electric field is a special kind of matter that exists around a conductor with an electric current. But the good thing about this definition is that, in general, it doesn't actually answer any questions. Meanwhile, the electric field is one of the fundamental concepts that, in fact, is supposed to clarify the mechanics of many physical phenomena related to the concept of electric current. But unfortunately, there is still no direct definition of the electric field or a clear, unambiguous understanding of this issue in science. And that's exactly why we're moving on to the next episode in the series Nobody Knows What Electric Current Is. This is Yuri Trifonov, and today we're going to delve into the electric field. In order to somehow imagine what an electric field is, we need to go back to what is generally called a field in physics. And this is where, let's say, the real fun begins. The thing is, there isn't really a direct definition of a field. And almost all fields are characterized in much the same way as we define the electric field with the standard definition. It's a special kind of matter that exists in one form or another. By the way, there was a big video on the channel about physical fields as phenomena. I recommend watching it, and there will definitely be a link somewhere here in the description or maybe up there in the suggestions, depending on where you see this video. A physical field, broadly speaking, is a way to describe a particular physical phenomenon at a point. For example, there's such a concept as a temperature field. It's much easier to imagine than an electric field. And the temperature field describes how the temperature is distributed throughout, let's say, the room. For example, right now there's a heater running in the room. This heater warms the air, takes in cold air from near the floor and pushes it upward. At the top, our temperature field shows higher temperatures, while at the bottom it shows lower temperatures. And if you draw a model of the temperature distributed throughout the volume of this room, marking the value of the temperature at each point, then what you get essentially is a temperature field. In general, in theory, all physical fields are tied to this very phenomenon. From here, another interesting question arises. Is it possible to consider that, in general, all fields in physics, or various fields, are of one kind or another of matter? Here we run into a very complex and not at all clear theory. On the one hand, it's hard for us to deny that this or that field is capable of affecting various different types of objects. We remember that if you, say, vigorously rub a plastic comb against your head, then from a certain distance you can noticeably influence and attract pieces of paper laid out on the table. And by what means do we influence them? As a matter of fact, we exert an influence upon these pieces of paper precisely because the field is capable of transmitting an effect from one object to another. And with all of this, the field is therefore a physical, material reality. After all, imagine that you take, say, a pump and inflate a bicycle tire. When you press down firmly on the pump's piston, the piston compresses the air inside. You will feel a very noticeable resistance to moving the piston further, making it quite hard for you to pump up the tire. And you suddenly realize that the air trapped inside this pump is actually a physical material. The air, in this case, actually transmits the pressure from one point to another, and you can feel how the pump's piston presses against the part of the pump where the hose is attached, which then transfers the pressure to the tire. Based on this, we can conclude with certainty that such an air field is, without a doubt, a highly unique and distinct form of matter. If we return to more complex fields, such as the electric field, magnetic field, or gravitational field, the situation becomes much more interesting. Detecting a particular field in the way we pump up a tire is, let's say, not always possible. And if it is entirely possible and feasible to do so, then we will be determining that very effect by transferring the interaction from one object to another, and what we will actually perceive is, once again, that very parameter which in fact we were measuring. I've said a significant amount of information and most likely you're confused. And that's perfectly fine because there really is a lot of confusion here. In fact, if we are trying to successfully identify and detect a particular physical field, we use one method or another for detection. For example, to detect an electric field, we have a number of fascinating and highly effective techniques. They are all standard, and I think there's no point in talking about them right now. But there is one important thing in all of them. When we use such techniques, we are in fact not detecting a special kind of matter, but rather we are detecting some effect that exists at a point. Those who regularly watch my videos probably remember that physics in general has a certain problem with distinguishing the material from the immaterial and where to draw the line between matter itself and, for example, energy. By and large, as we found out in recent videos, all physical matter is a special form of energy, and it's hard to argue with that. And also, that gentleman hanging on the wall used to say that for us, matter is equivalent to energy. And here too, there's a very big and complex theory, which there's no point in diving into right now. But we can extract one thing from this. In physics, any matter is associated with energy, which means that there is no clear boundary between matter and non-matter. And that means the definition we formulated at the very beginning, that a field is a special kind of matter, actually suits us quite well. With a number of assumptions, of course. And the assumptions are quite straightforward and simple. You shouldn't visualize or imagine a field as jelly, a cloud, snow, water, or any other similar substance into which an object is immersed. Such an idea is perfectly reasonable and acceptable when we're dealing, let's say, with simple fields, like a temperature field. But when we deal with complex fields, like the electromagnetic field, such a direct comparison will often lead you to the wrong conclusions. Therefore, as I already mentioned in the video about physical fields, it's much better to think of a field as a certain mathematical model. This mathematical model essentially allows us to divide space into certain sectors, to draw that very well-known, that mesh-like representation, to draw this grid. You've surely all seen this, and I'll show the picture now. And by means of this kind of, let's say, partitioning of space, it becomes possible to describe how a particular physical phenomenon manifests itself and to what extent at any given point in space. And based on this in general, you can sort it all out in your mind and say, let it be a special kind of matter, let it be whatever you want. But what is crucial for us is that in this case, with the help of the electric field, we can accurately describe the effect of this field at a specific point. And this is where the biggest confusion begins. We said that there is an electric field around an electrical conductor, and the electric field allows us to push the particle forward. But the electric field is created by moving charges. There is a problem. The problem is already obvious. If the charge is not moving, there is no electric field. And if there is no electric field, then the charge does not move. So we end up with a chicken and egg problem. No, well, of course we can resort to other explanations. We can say that there are positive and negative charges, that they interact in a certain way, that opposites attract, and when these opposites start attracting each other, the charges begin to move. And in this way, they create an electric field around themselves, which then helps them continue to move. But with all that, a question arises. In that case, it's not the electric field that pushes the charge, but some other interaction that causes this whole. The mechanism spins and the pendulum swings. At the same time, the question becomes even more pressing. What exactly is the charged particle that moves through the conductor? And it's even harder to figure out what, in fact, an electron is. But we run into the electron again because in most cases it is electrons that are the carriers of electric current. In the conductor, and in fact it turns out to be a very tangled and complex construction. The field somehow interacts with some unclear objects and somehow acts upon them. Moreover, the objects themselves provoke the appearance of this electric field. But we can turn to quantum theory, and quantum mechanics, manages to get out of this situation quite well. And in quantum mechanics, if you don't know, or perhaps as you remember, there is a separate field for each type of interaction, for each particle. At the same time, it is emphasized that the particle itself is a disturbance within this field. When such a surge occurs, we again draw that same model. If you remember this interesting object, I'll show the picture now. And we say that within the field there is a disturbance, a deviation from the zero position. And this field allows for the generation of a particle that moves along the conductor. In this scenario, there is nothing complicated, and there is even a certain logic to the fact that we have transferred energy to this field. The field generated a particle, or more precisely, manifested itself as a particle and made part of itself vibrate, and this vibration is transmitted through this very field. Everything here is completely logical. Then it turns out that the electric field, let's say, is a mathematical object capable of describing the distribution of energy and possessing certain properties, and at the same time allowing a certain particle to be generated within itself to make this particle move for one reason or another, or essentially to describe the interaction of this energy that we have at the moment in the field with whatever at some point enters this field, is immersed or ends up there, and then we can quite easily describe the strange behavior of the field that we observe from time to time. What do we mean by strange? It means that if you end up in a field with high intensity, there's a chance you'll get shocked by electricity. And if you don't know, it's not at all necessary to touch a bare wire from time to time to get an electric shock. Sometimes it's enough just to be in a field of high intensity. Well, can we observe how electric and electromagnetic fields work? In a very simple case. Basically, all you really need to do is ride a bicycle. Find a spot under a power line, preferably a high voltage power line. And then you will feel, for better or worse, exactly how your entire bicycle starts to hum and vibrate. And in the worst case, you'll start to feel tingling from the handlebars, the seat, and other exposed metal parts of your bicycle. As a matter of fact, based on the logic we've just described, we can now comprehend and determine how it is possible to describe a particular field, a physical field, and in this case, an electric field, using those very complex, those three-tiered, intimidating formulas that you've surely seen in standard physics textbooks. One way or another, this strongly underscores the fact that we are not dealing with some unique form of matter, which is often presented as a fundamental building block. Rather, we are dealing with a certain mathematical model which essentially allows us to describe the distribution of energy. Now you might say to yourself, well, you keep talking about how all these different fields are, let's say, just a specific form of energy distribution. So why then do fields not act the same way? Now this is actually a very good and indeed a very complex question. Unfortunately, at this point we are not really able to answer it, but we can say one thing. The only thing that distinguishes an electric field, for example, from a magnetic field or any other field, is the particular manner in which energy is expressed and manifested throughout space-time. And I think it is quite difficult to really argue with the undeniable reality that, essentially, if we pass energy through a particular model, that energy will take on a specific form. By the way, everything once again ties back to what I was saying about matter. Be sure to watch that video. And it was pretty much the same thing there, because essentially any electron, any particle, and any object are all represented by energy. And the ability of a particular particle to exist is precisely the ability of energy to interact with a field. So what are fields needed for then? Fields are needed to find some connections that might exist at all, to find loose ends in this complex theory. I wouldn't rule out that after some time, the idea of fields will be abandoned, just like the idea of the ether was. But you know what's interesting? When you analyze this simple and naive definition about a special kind of matter, you realize that most likely you won't be able to come up with anything better, at least for now. And it's actually the right thing to say to a 5th grade student who hasn't seen any of this yet, or when students first start studying fundamental physics with electricity, probably in the 8th grade curriculum. Then, in fact, for a typical high school student, you really can't come up with a more suitable definition than a special kind of matter. And for us too, when we've already encountered and examined all the other aspects, it's sometimes still incredibly useful to refer to it as a special kind of matter for one very simple and clear reason. If you, damn it, get yourself into an electric field, you won't care what exactly hit you, why a particular potential discharged on you, or why in fact you got shocked by electric current. You'll just imagine that you've gotten into some kind of terrifying matter, which essentially is what gives you an electric shock. Well, for now, there's only one thing we really need to remember. The electric field is a fundamental concept for all of electrophysics. So, having even a rough, basic understanding of what an electric field truly is absolutely essential for us to continue our journey into this subject. That's why this video is, in fact, one of the very first in our series. No one knows what electric current really is. And it is to this video that we will refer in the future, just like the video about electric charge. And as a matter of fact, we've already discussed what electric charge is. Now, we're looking at what an electric field is. We've also said a few words about electric current in previous videos. And generally speaking, from here we can move forward and explain how the electric field moves charge through a conductor. This question is also complex and requires a special, separate understanding. And one more thing before we finish. If you remember, the project has a Boosty page, and there you can ask questions. But it turned out that not everyone finds it convenient to register a separate account on Boosty. That's why I created another convenient tool, and the link to it will be in the description. There you can not only support the project, but also ask a question, which I will definitely answer. I try to read the comments, especially on Zen and especially on Telegram. On YouTube, I hardly have time to do this. And if there's an interesting question there that I am able to answer, I try in fact to respond to it. But many questions just get lost in this abyss. This abyss of, I want to say, informational garbage, because sometimes people write all sorts of nasty things, and it's unclear why. I have to delete all of that, and I don't always have time for it either, but that's not the point. So my friends, if you want to make sure your question gets answered, then write it along with a donation using the link in the description, and I will definitely answer any question in a donation. When we have accumulated a certain number of different interesting questions, since questions often repeat, we will make a separate video and do what is usually done on streams on other channels. Right now, doing streams is a bit problematic, so this is how we'll proceed. We'll simply make a video with answers to your questions, which you're sure to enjoy and find interesting. And once again, all you need to do is send a donation with your question, which will support the project and guarantee you get an answer. That's all for now. Thank you very much. Let's stay in touch and see you next time.